Not yet.
Can you see the slide?
No, no.
Okay. Let me to come back again. Sir, I will try to connect again. No, I mean try to share again.
Sure.
So now, are you able to see my screen?
Yes, yes.
Okay. Yeah. So I think there was a question on slide 16 that why the responsivity is going down in this region. So as I said, silicon is an indirect bandgap material. These wavelengths meaning very high energy. So we come up with a photon which has very high energy. So the photon, what it will do is that it will generate some hole at this location. Electron will go here because the photon is now absorbed, right? And this electron, this particular electron, it has very high energy. What does it mean? Meaning its kinetic energy is very high. So what it can do, suppose it's a silicon. So silicon also has a crystal structure. So there are other bonds as well. And if its kinetic energy is so high that it's kind of uncontrolled, so it will try to collide with others as well. And once this collision happens, this happens through phonons, or simply say that it will lose whatever energy it gained through this kinetic energy, which it got from this photon. It will lose all this energy in terms of heat. So the temperature inside the crystal will increase, or inside the semiconductor will increase, but it will not, give us electron hole pair which will come out and go towards the battery. So it will not give any contribution to the photocurrent. And if it is not giving any contribution to the photocurrent, if it is a non-radiative process which is dominated by heat, then responsivity will not increase, because this is simply, if you want to increase it, you have to increase the current value, and the current will increase simply if you have more electron hole pair which is coming back to the junction. But in this case, electron hole pair are getting generated, but the problem is they are not going to the junction. They are just stuck inside the material itself, hitting somewhere here and there, and then just the energy is lost in terms of heat. That is the first problem, that the as soon as you have higher energy, the responsivity is going down. The another problem is that for lower wavelengths, the absorption is quite high. Because the absorption is high, the photon, as soon as it comes, it gets trapped At the surface of the material itself, it doesn't get time, to go inside and generate a lot of electron hole pairs. So automatically the responsivity will go down. So as I said, it's very important that you know that doesn't matter how many electron hole pair we create. It all matters how many of them we can take them out of this material and into the circuit, and they should go here. This is what actually matters if you want to increase the responsivity. Even if there are 100 of electron hole pair you are generating, with a lot of photons incidenting and lot of electron hole pair generating, if you are able to extract only out of 100 only 2, then your responsivity is very poor. But if suppose only 40 is getting generated, and out of 40 if you are able to extract 20 of them, then your responsivity will be quite high. So it doesn't matter how many photons are getting absorbed. You see my point. Once they absorb, electron hole pair are generated. It is very important that they come out into the circuit and contribute to the current. That is the main point. Uh, so yeah, now let's go to the rise time and the bandwidth of the detector. So what it simply means is the response time, meaning I have the detector, I hit with a photon. How much time does it take to give me that current value? Does it take 5 minutes, nanosecond, femtosecond? So that is the kind of the response time. So what happens here is that we hit with the photon and the electron and holes are getting generated. Now see, this is the positive terminal. So I did not tell you this story because otherwise it will become complicated. So what happens, because of here we have a positive terminal, so there will be a positive charge accumulated here and there will be negative charge accumulated here, right? This electron will definitely get some attraction in this side and it will pass through this, and then it will go to this terminal. The hole, it will go through this and it will come here, right? But since you see there is a negative charge and there is a positive charge, so there will be definitely electric field will be generated. Usually we call a potential, which is a barrier potential, and because of that potential, there is electric field within this depletion region. This is very common because now we have consider them, these two have kind of like charge plates. So one plate has a positive charge, another plate has a negative charge. So it's like a capacitor, um, two plate capacitor. Epsilon A by D is the capacitance, where A is the cross sectional area, D is this distance, right? So this is called this junction capacitance. So we have now, then this electron hole pair will go and then they contribute to the current. So finally we have this current value. So actually this whole process happens within nanosecond or picoseconds or microsecond, whatever I have explained you, right? And that is the time actually which we say is the detector rise time. How much time it takes to come out into the circuit. So how to decrease that time? Because if you decrease that time, that will be, let's say, very good or fast detector. If this time is too much, then it's the slow detector. But you have to see on which parameters this time is dependent. Um, so let me let me show you here. So suppose we have created some electron and hole pair. Some photon is absorbed. Now suppose this electron will go in this direction, right? First, it will pass through this depletion region. But you see, we have a barrier potential. So we have some sort of electric field present in this region. This field will help to go this electron with a faster speed. So we called it a drift current. Now the same electron will also pass through this n side where there's a lot of minus uh, minority or majority carrier is negative, and then electron will somehow diffuse through them and then it will come here, right? So this is called this diffusion current. So as you can automatically see that here we have this electric field because of this barrier potential, which is helping electron to pass through this. So the drift current value will be higher and the diffusion current value will be lower, right? Um, so suppose if you want to make a detector, what would be our preferable choice? The preferable choice is that this area should be as big as possible. So my drift current is higher, meaning electron passes very quickly and then reaches towards the junction or towards these copper wires, right? So I should try to make this diffusion current or this length as small as possible. Then my detector automatically started to work faster, right? So that is the basic behind this. Uh, but now, how can I increase this current, which is dependent on this barrier potential? So actually, this barrier potential is dependent on this outside potential, the battery we apply here, V naught. Uh, so the reverse bias voltage. So one answer is that increase the reverse bias. If you increase reverse bias, the barrier potential will increase. If the potential increases, then the electric field here will be higher, and then definitely the electron hole pair which are getting generated, they will move with a faster speed, meaning we have a fast detector. So increase V naught, but how far we can increase it? We can increase only up to a certain level, which is the saturation voltage. Once you cross that voltage, the junction will break down. We cannot do that. So there is a limitation with that. Um, Also, you have to remember that electron and hole, they have different mobility. Electron moves faster or holes move slower because one is heavy, one is less heavy. So this also one has to consider, which I have not included here in the talk. Otherwise, it will become even more difficult to explain. So, but you have to keep in mind that the story is same. What I have explained for the electron, the same will happen for the hole. But just remember that both does not have the same mass, so the velocities will be different. Um, so this is the one aspect uh, that try to decrease the diffuse current, try to increase the drift current by increasing this depletion width or by increasing V naught. You will have a good detector with fast response, good rise time. The another thing mm, is RC time constant. This also defines how fast the detector behaves. So what is RC time constant? Remember, this is a photodiode, right? I have just applied, I have taken a PN junction and applied a reverse bias. But in reality, this is not how we use the photodiode. We have to use this photodiode in combination with some circuit, you know. So there will be some resistance towards which you can measure some sort of current or voltage. So for example, this is NP junction and this is the depletion region, and I have now connected it in a reverse bias, and I take a resistance here and I try to measure some sort of voltage. So as soon as I hit with a photon, you see that I also create a junction capacitance, which I explained you here why there is a junction capacitance. So we have R and we have C. So if I try to make an equivalent electrical circuit to this, that will be RC circuit. And you know this RLC circuit, RC circuit, LC circuit, all these circuits have their own time constant. So for RC circuit, uh, that is the value for the time constant, which is dependent on R and the value of C. So this usually, typically here, people use 50 ohms of resistor. You can use a different resistor, doesn't really matter. But the point is that the electron hole pair generated here, they will take some time to cross this, and then they will come into the circuitry, the real circuit. This is the transit time. uh, it depends on the diffusion current, it depends on the drift current, which depends on the material or on the V naught. on the on the depletion length, that's the different thing. Once you start using this photodiode, there is another time constant, which is this RC time constant. We also have to consider that. So we cannot do about this RC time constant. It will be there. It's dependent on the C, dependent on the R value. But what we can do, we can play around here. So when a device engineer works, it mostly works on this. It's called T transit time. How much time the generated pair takes to come out of this PN junction. So this value, this time constant tau r is 2.2 time RC, usually dependent on R and C, which we hardly can change. So this will more or less remain the same. We can play around here. So there are two things which define the rise time. One is the called transit time, which depends on the time taken by electrons to reach the electrical constant, and the second time is the RC circuit time constant. So combining these two, you will get the total rise time of your photodetector. Um, so this is the total time, the transit time, which comes from this, and the RC time, which comes from this. So that's the total time. Now suppose we have this PN junction. It's in the reverse bias, and again we have this resistance R. We hit with a photon, and we have this capacitance. I told you that there are two major contributions. So if I want to reduce this transit time, um, what I can do is somehow do something that it comes out very fast from this region and get into the circuit, the electron hole pair. So what people think is that increase this length, and then why should we increase this length? Because in this particular case, the time electron is spending here is more as compared to the time which is spending here, because it has to go through a lot of this diffusion process within that material. So what happens if I make this length bigger and I put some intrinsic material? Now the electric field is present in like this in the whole region. And before, the electric field, which was due to the barrier potential, was only here. So this electric field is helping my electron not only in this much area, but now within this much of area. So definitely what I have done is I have increased the drift time. So now the drift time has increased. Uh, and this is the reason that people mostly use the pin diode, that now your drift time is increased and your diffusion, it's somehow now roughly equal to the diffusion time. Um, and that is the reason we use pin diode. So because now it's a fast detector as compared to the PN diode. So drift is more, diffusion is less, and faster the response. Uh, but here is the catch, or here is a trade-off. So think in a way. Suppose you want to design a detector. Actually, overall, you want this complete width to be small. Smaller the width, faster will be the response. But as I told you, we also have to consider these things, that this is the desirable thing, that my drift time should be equal to the diffusion time. Uh, so I have two things. First, I want my device as small as possible. Why? Because if the device is bigger, definitely I have more diffusion happening and more collision happening. So the overall aim is always to make the device smaller. Um, but do it in such a way that your drift and diffusion time remains equal. But don't you think it's counterintuitive? Because I just told you that if you want to make these time equal, you have to increase the W. Uh, so uh, then that is the problem actually. That if you want to make your device dimensions very small, uh, and at the same time you also want that the diffusion and drift time should be more or less equal. That's why you are using this pin diode, um, so that your responsivity equation, you remember I also said that increase the W value, increase the alpha value to get the higher responsivity. So it is in a way is useful that alpha to be large and W to be large. But if you make the dimension larger, it creates the problem because your detector itself automatically becomes slower. Um, so if you reduce W, you get faster response, but your responsivity or the conversion rate decreases. You see this point, right? So if you reduce W, right, what happens if you reduce W? That your responsivity value uh, will be decreased, right? From this equation, you could see that. Uh, so there is a trade-off that smaller W meaning less absorption because less photon will be incidenting. Bigger W meaning you have more active area, bigger depletion region, more photons can be incidenting. So it's good. Let's make with a bigger W. But as soon as you make the W bigger, the problem is that your responsivity will be uh, decreased. But you can do a fast detection, so meaning your bandwidth will be very high. Uh, Similarly, suppose if you take a larger W, which means you have a very good absorption, then the responsivity will be high, but you will definitely do a slow detection. So it's very difficult to make a photodiode which can do both things together. It can do very fast detection also, and it can do for a higher responsivity. So responsivity and the detection, uh, there is a trade-off between these two. Only one can be done at one point of time. So that is about this rise time. Now I would like to explain you a little bit about single photon detector. This is something in quantum world. This is very important actually. So here is just some examples. So what do you think a single photon, which is coming from a laser, which is 633 nanometer helium neon laser, what is the power of a single photon? So you see the energy is roughly 10 to the power minus 19 joule, and if you consider power in a 1 nanosecond pulse, the power is 10 to the power minus 10 watt. So you just have the energy, you have the time, you just divide, so you will find out the power. So power is quite small for a single photon. So suppose a pulse is there, it's a nanosecond pulse. This pulse contains only one photon. This photon is of 633 nanometer. This photon will be having this much of power, right? Now you think that which detectors will be able to detect this kind of power, 10 to the power minus 10 watt. So let's see how much noise we have in a detector. So for example, due to the thermal noise, which is Boltzmann constant into the room temperature, or in this case, it's a room temperature is 300 Kelvin. So we have reduced the temperature; it's 77 Kelvin, and you see that this is not very small as compared to the photon. So photon has power minus 19, it's minus 21. Uh, but suppose if you increase the temperature, if you make it room temperature, it will become very difficult for normal photons, normal detectors to detect a single photon because the energy and powers are very low. So that is the reason people use this avalanche photodiode, or there are different type of diode which I will explain you in a minute. So um, most of you are aware about avalanche photodiode, so I have not included that. But I want to give you a little bit information about SNSPD. So these are superconducting nanowire single photon detectors, and these detectors are able to detect uh, very quickly, and they can do from UV to mid infrared, and they work at very low temperatures. So 1 to 4 Kelvin. You know that the minimum temperature which can be achieved is 0 Kelvin. So they are really very close to that. And what happens here? So let me explain you. So number one, you look at here. So that is consider this is a superconducting nanowire. What happens, suppose one single photon hit to this superconducting nanowire. So one single photon is hitting. Now what happens, because this was in a superconducting state, as soon as you hit with a single photon, and this photon has some sort of energy associated with it, and because of that energy, now the superconducting state is broken. So what happens is that it will break the Cooper pair, and this Cooper pair will be break, and then you have a cascade effect, and then there will be more electron hole pair getting generated, but this generation will be restricted in this particular direction. So you see that in the state 3, since now the superconducting state is disturbed because you hit with one single photon, which has now created some sort of resistivity, and now this resistivity actually drastically increases for a very short period of time, and it goes up to kilo ohms. So you see that it now increases in this particular direction. So this is time evolution, that beginning, and then slowly you see in the whole patch, the superconducting state is destroyed, the Cooper pair is gone, and thermalization happens, and then you have a lot of electron hole pair. Now what you do, because of that, now you connect it with a bias, and then you take all the thermalization to the ground, and you detect the current value. So what happens at the state 1, in the signal there was no current, and then slowly at state 2, once you hit with a single photon, uh, what happens after that, this cascade effect or thermalization happens, Cooper pair breaks, and then the more electrons getting generated, and suddenly there is a very high resistivity, and this all happens within a picosecond of time, and then you can detect this signal. So this is state of the art detectors which are being used at the moment to detect a single photon. So I just wanted to give you a glimpse of it, and that what is currently being used to detect a single photon. And the price of one of this detector is 120k euros. So 120, three more zeros, multiply by 90 or 100. Now how this superconducting wires look like. So that this is the SEM image, and this is how this whole detector looks like. So these are superconducting wires. They are actually, they start here and then they go in this particular shape. So if you zoom in, you see this is some sort of like a grating structure, but in a zigzag way. What is this material? So they usually use niobium nitrate as a superconducting material to make these kind of detectors. So there are some emerging trends at the moment that people are now moving also towards 2D materials and using them as detectors. People are also using quantum dots and making photodetectors. The another trend is to do integrated photonics, like take a chip and make a detector onto the chip together with the light source, and then do all the photonics on a chip, not on a breadboard. So that is all about integrated photonics. And also I told you about these hot electrons, very high energy electrons. They are also being used for catalysis application. So here I will give you one of the experimental example from my lab work, and we will try to create a Schottky photo detector. So here the aim is that we have a target substrate. This could be a glass slide, this could be a metal surface, gold, TiO2, whatever. And what I want is I want to place some gold nanoparticle gratings or 1D lines of gold nanoparticles onto this substrate. How do I do that? First, I start with the photoresist. I make some gratings on top, and then I convert these gratings into a PDMS. So that is a soft material, like rubber kind of material. So whatever I have created here, I have created a replica of that material onto PDMS, and then I take my target substrate, whatever it was, semiconductor, insulator. I take that substrate, I put a solution of gold nanoparticle and press it. And finally, I have these uh, 1D lines or gratings of nanoparticle on top of my target substrate. So I will show you the case where I have a glass substrate. And on top, I have deposited titanium dioxide, and this deposition was done with E-beam evaporation. And on top, you have nanoparticle gratings. So actually, what you have is a semiconductor, and these particles is gold, so metal. So you have created a metal semiconductor junction. And now what I do is I deposit electrodes on top of this sample. So I deposit electrodes on top, and then I apply some voltage. And what I want to see is how much is the current flowing through this channel. So this, you can say, source, this is drain. You have applied 1 volt, and how much voltage or current is coming. But before that, um, so this is how this sample looks like in reality. That is a glass slide. You coat it with TiO2, so it looks somehow pinkish in color. And then this is the region where I have these gold nanoparticle lines. And what you see here, these are these electrodes which I deposited on top. I said there are some electrodes on top. So this is one set of electrodes. This is the another set of electrodes. And if you look at the optical microscope, so this is electrode. This is one gold electrode. This is the second gold electrode. This is third one. This is fourth one. Now what I have done is I take 2 of these, I apply particular voltage, and then this becomes the channel length. So roughly this channel length is 350 micrometer. And if you go in between these electrodes, if you zoom in here with some scanning electron microscope, you see these lines. So this is gold, these spherical particles, and they are sitting on TiO2. Now what I want to do is I want to shine some light on top, and what I expect is that because it is a metal and here is a semiconductor, so I have created a Schottky junction. And once I incident light to the metal, lot of these hot electrons or the electrons which has very high energy, they will be created. They will go to TiO2, and then they will increase the conductivity of TiO2, and I will measure some current. So actually, this is how we usually do it in the lab. So this is a stage, and I told you that I have deposited electrode. So this is this electrode, this is the second electrode, and remember this one electrode, the second electrode, I apply some voltage. How do I apply the voltage? So there are these tips. You could see these tips. This is a copper barium, very soft tips, so they don't scratch the electrode, and I touch them. So actually I can move it up and down. So I touch these two, and then I started to. So there is a 2 probe station here, and I apply a voltage, and then I see how much current is coming out. So here's the current which I can see. So for different wavelengths, I see the current values. So on y-axis we have current, on x-axis we have time. So what I'm doing is I'm giving voltage for 20 seconds, then stopping it. So this is the time where I have given the voltage. This is the time where I have stopped the voltage. Then again I give the voltage, then stop the voltage. So I create the cycle, on-off cycle, on-off cycle. So let's look at 565 nanometer LED. I shine this LED, and then I see that some photocurrent 3.5 nanoampere is generated, and then this current is also kind of going down. But you see see my point that in the lab we can actually really make a device and calculate the photocurrent. Now remember, for responsivity, I told you the formula. This was somehow related with this 1240 divided by the lambda. J is the photocurrent per unit area, and P is the incident power. So if for this particular device, if I want to calculate the responsivity or IPCE, incident photon conversion efficiency, like how many photons are getting converted into electrons. So anyways, it is the responsivity, just written in a different way. Um, so in this formula, what do I need? I know the lambda because I know it's 565 nanometer. The power input, actually, when I purchase the LED, I can just put the LED in front of the power meter, Also, the seller always gives the specification, so I know what is the power of my LED. But you can also check, take a power meter, calculate the power. So this also I know. The current density. So I know the current. Now what I need is the area. So actually, if you consider this as a source and drain, so you have to take this particular area. So just assume that uh, you are incidenting this light on the whole part. So just try to take this much area what you are incidenting here. That will become your area of interest, and then you divide this current value with the area. You get your J value. You have your P power, which you know of this LED, and you have the wavelength. So we have all the things. We can actually calculate the responsivity. And here's the responsivity with respect to the time for 565. For 565, there is more current. We get higher responsivity. For 590, you see this orange color. The current values are lower. So we anyways get very low responsivity values. So it's not a magic. You can actually create all these devices in the lab, and then you can also try to maximize the responsivity and their NEP and so on. So now in the last minutes, I would like to go towards the noise. What is noise? So actually, signal is something which is wanted, and noise, which is something which is unwanted signal. So, for example, this is y-axis, this is x-axis, and this is, let's say, some sort of noise in any signal, right? And it's random in nature. Uh, but suppose if something is random and still you want to know about it, what would you do? So if some random person comes to me and I remember the face, um, what else I can do? I try to trace it back, like what kind of shirt he was wearing or she was wearing or something like that. So similarly for electrical signals, what you try to do, suppose you get a random signal, there are two ways, either to deal with them in time domain or to deal with them in terms of frequency domain. So if you deal with the random signal in time domain, we actually talk about probability distribution function. And if we deal in terms of frequency domain, we talk about power spectral density of this particular function. So there is a noise which is random in nature, and we want to know about it, we want to deal with it, we want to reduce it. But before that, we would like to know like what kind of nature of this noise has. So actually, what you could do, suppose you have a noise signal. This is voltage versus time. So in time, this is random fluctuation. You could actually create a probability distribution function of this noise signal. So on y-axis, you have probability and voltage, and then you could have some sort of, idea about it. So this probability function, if I try to draw, it looks maybe like kind of a Gaussian function. Now what happens is that at least if I know what is the mean value, so I could say that the mean value will be like this. And if you know some variance, then you could say that okay, if this is my noise, then this might have a mean value somewhere here, and maybe this is the envelope where the noise is changing. So it's not, there is no point. It's very less probable that the noise will go out of this particular value, the variance value. So at least by doing it, I know something about the noise. I have done something. Um, so this noise is not very easy as it sounds. Actually, there is a lot of statistical mathematics behind it to understand it, and even to convert a voltage signal into a probability density function or power spectral density. That's a whole different electrical engineering subject. But just to give you a brief idea that you have to deal with some sort of statistics when you try to deal with the noise. So here again, this is this probability distribution function where mu is the average value and this is the variance. Um, so Actually, there are two very famous kind of distribution. One is Poissonian distribution, and the second is the Gaussian distribution. So in Poissonian distribution, what happens is that your variance is equals to the mean value. And the Gaussian, Gaussian is when it's kind of a mirror symmetry towards the y-axis, but in this case, it's not the mirror symmetric. So we have a noise signal, we can create a probability distribution function, and this function can be of Poissonian distribution or Gaussian distribution, um, depending on what kind of noise it is. And then once you have the variance, you know that how much fluctuation in the noise can happen. So this particular signal can have maybe noise amplitude which can go maybe up to these levels. There is very low probability that something comes up here. So the probability might be less than 0.1, that some voltage value for the noise comes out in this region. So just briefly, what is this Poissonian distribution? Um, so here is this I have taken from a mathematics book. So here is the equation for Poissonian distribution, where this n bar is the mean value. So you take the nth power of the mean value and e to the power minus mean value divided by n factorial. And the variance is also equal to the mean value. So this is called Poissonian distribution. Now suppose here on the x-axis we have numbers and on the y-axis we have probability. So let's say if we have only two events, one with this much probability and the second one is with this much probability, the overall average will be 0.1, right? Uh, then if you increase the probability here, um, if you increase the number of events, you see that slowly, if you start increasing the number of events, the Poissonian distribution try to converge towards the Gaussian distribution. You remember this is how it was for Gaussian distribution. So this Poissonian is nothing but when you tend towards higher frequency values or higher average values, it will tend towards the Gaussian distribution. So this was, let's say, some recap from the mathematics. But now let's come back to the main noise, which we usually see in the electronics. So very first is thermal noise or Johnson noise. So why this noise happens? Because there are a lot of random electrons which are present in any resistor, capacitor, in all these circuits. Um, so they create this thermal noise. What is the formula for this thermal noise? So this is dependent on Boltzmann constant multiplied with the temperature. So at room temperature, this value might be quite high. And what is delta F? Delta F is the bandwidth and R is the resistance inside the circuit. So suppose this is the resistance 1 kilo ohm, and you have applied some voltage, and now if you see across this resistor, ideally it should look something like this: 1 volt divided by 1 kilovolt. This is the current value, but actually the current is not like this. You will see actually the current coming out something like this. And what are these fluctuations? These fluctuations happen because when the current started to flow, there is also a random thermal motion because of this kBt value, so the randomness um, associated with the temperature. So thermal noise is actually white Gaussian noise. What does it mean? Um, White noise meaning the noise which does not depend on the frequency. So whatever is the wavelength or whatever is the lambda, it will always be there. And if you plot a histogram in time, uh, it will comes out in terms of a Gaussian plot. So that's why we call it a white Gaussian noise. It depends on the temperature but doesn't depend on the frequency. So on the x-axis, if you have frequency, so you see this will be the total power, or this will be the total noise, if you see, which is 4k TR inside a circuit. The second is the short noise. So short noise is the when the photoelectrons are generated, they are generated at random movement, and then also they arrive at the junction at random time. So because of that randomness, the short noise comes into the play. So let me explain you. You remember this diagram which we use. This is the reverse bias junction. We have electron hole pair, and the photons are incidenting, right? The photons are incidenting. Where does this photon come from? So there might be a laser source, there might be some other incandescent lamp or something. Now think about it. Suppose you have a conduction valence band, conduction band, and you hit with some sort of photon, uh, which kind of like the pump frequency. Suppose you pump, and then this electron goes to the high energy state. Once it will come back, it will emit a photon, right? How do you know that when will it really come back? Because it's a spontaneous decay process. You don't really know that even if you have pumped the electron, when exactly so there is a relaxation time, but within that relaxation time also you don't really know at which exact instant the electron is going to come back. So that automatically creates a randomness. It's by nature the process is random. Now the thing is, if the coming of the photon is random, then the way they will create electron hole pair and at the time they will arrive at the junction, this will also be random. So this randomness is called short noise. And again, this is also a white noise because this is not frequency dependent, because this all randomness is inherent by nature. This is not coming due to some frequency. So if you look at the statistics of this particular event, this is Poissonian statistics. So this is not Gaussian statistics, this follow Poissonian statistics. And if you look at the current value which it contributes towards the circuit, so suppose there is no incident photon, nothing, but still you would see some sort of current coming out. So this is because of the randomness. Now you might have seen detectors, and we usually cool these detectors. Like if you see in the real lab, we cool the detectors, but the point you have to understand, why are we cooling them? So ideally, I told you, we can go in this world, we can create a temperature as low as 0 Kelvin. We cannot go below that. um, in a fridge there is temperature minus 15, minus 10, but how do we create, let's say, a very low temperature? So there are ways to do it. People use liquid nitrogen, which can create 77 Kelvin, but it's still not 0 Kelvin. Just to give you a reference, the room temperature is 300 Kelvin. The another technique is to use liquid helium, which can create 3 Kelvin of temperature. And there are very expensive refrigerators used in quantum computers. They are called dilution refrigerator, which can actually create, so ideal is zero, remember. So it can create 0.003 Kelvin. So if you take example, suppose hypothetically we have a bandwidth of 1 gigahertz and we have a resistance of 50 ohm, then how much at room temperature, how much dark current we can generate? So we can actually generate 0.5 microampere. So the dark current values are in microampere at room temperature. As soon as you use liquid nitrogen, you reduce the dark current value. So it drops down up to 2 times, 3 times. So that is the reason people actually use coolant, or they cool the detectors with some sort of cooling. And in the end, there is another third noise, which is called the flicker noise. And this noise happens due to the imperfection or these trap state and surface defect. And if you want to reduce this noise, as I told you in the beginning, try to make your semiconductor material as pure and as good as possible. This noise actually happens at low frequency ranges in kilohertz, megahertz, not in the giga and terahertz ranges. And this depends inversely to the frequency. So it's very high for lower frequency. And the noise amplitude is actually dependent on this equation, which I'm not going to discuss the derivation of the equation, but definitely it depends on one of the frequency. So the important thing you have to remember, that is inversely proportional to the frequency, and it's very dominant at lower frequencies, and its distribution is also non-Gaussian. It looks something like this. So if you plot on the log scale, this is how it will look like. And so in summary, today I told you a little bit about the semiconductor-based photodetectors. I told you about superconducting photodetectors, and we discussed about responsivity, noise, rise time, quantum efficiency, and some applications. And in future, what people are looking towards is very fast detectors, which are smaller in size. As I also told you that there is a trade-off, and they also should be quantum enabled. And with this, I would like to thank you. And also, please, recently I joined this institute, so the location is pretty good. So please spread the words among your colleagues and students if someone would like to join our institute for PhD or MTech. So we are starting this new Center of Quantum Science and Technologies in IIT Mandi, and we are very happy to host new students here and maybe happy to collaborate with you as well. And these are some key areas where we work on. So mostly computation, and my topic is quantum optics and quantum materials. But we also do work on quantum cryptography and communication. And with this, I would like to thank Professor Avasti for giving me the opportunity to talk with you. And here's my email ID. In future, if any one of you would like to contact or have any questions, please feel free to ask. So with this, I would like to thanks.
Okay, so thank you, Dr. Vaibhav, for your wonderful talk. So there are, I think, few questions in the chat box. If you can have one or two, and rest, I will encourage people, they can post it, or they can directly email if interested. So I
Yeah,
can see
so
one question, if I remember correctly. Maybe you can just scroll the chat and respond one or two questions. That will be nice.
yes, sir.
One that I can see, thermal, short, and flicker noise are dominant noise source in the classical. Are they dominant source of noise for superconducting nanowires, SPDs?
No, actually not. So these superconducting detectors, they work at very, very ultra low temperatures where actually you can consider like ultra cold atoms. So the part of dark current and the noise due to the thermal barrier or due to the thermal impact is not there. So contribution from thermal is not there, but there comes the another aspect. Um, for example, if by some reason, if the temperature fluctuation is there, or by some reason, if you reduce the vacuum inside the chamber, that the vacuum goes up and down a bit. So as soon as all these quantum systems, they try to interact with the real world, they come up with different issues as well. So maybe not these kind of, uh, let's say, noises, but other noises started to come into play.
Mm, Another question, that is, can junction capacitance over limit the switching speed of modern transistors?
Can junction capacitance ever limit the switching? So at the moment not, but maybe in future might be might be possible.
Okay, so Dr. Weber, thank you very much for your talk today. And for the participant, we have also scheduled talk by Dr. Weber in this FDP. So he will going to introduce some new topics to you also. So we come to the end today. So I thank you all the participants for joining, and particularly speaker Dr. Weber Gupta from IIT Mandi for joining today's session and for this wonderful talk.
Thank you, sir. Thanks a lot.
For participants, we are going to plan the quiz by next week from the speaker's talk till Thursday. We will plan a quiz. So be ready for it Friday, and it will be open for, I think, 2 days for submitting the quiz. Thank you very much. And tomorrow also we have a scheduled talk, so please join the session tomorrow. Thank you.
Thank you. Yeah.